Hello everyone, I'm Tristan Oaks. You might be wondering what is in this pod which I carry, and as you can guess, it's ice. So maybe some of you have ever been out camping and it's like a snowy day and maybe you didn't bring enough water with you. So you had to heat up some snow and melt it for drinking, or maybe boil it for dishwashing. Well, today I'm going to be doing both of those things. So let me get this lid up. Alright, get the flame going. Oh, wait, let that burn off. Alright, so while we're waiting for that to get started, let's measure the temperature of this ice. Let that cool down. Turn this on. It's roasting probe. Go. Eesh. Might get burned. Come on. Oh, looks like it's almost ready. Alright. Looks like the ice is measly -1 degree Celsius, so it should melt pretty quickly. Alright, now I'm going to time this as well. So, here goes nothing. Now while that heats up, I might as well tell you what's happening. So, what I have here is a sample graph of some -100 degrees Celsius ice, 100 grams of it, and it gets heated up to 200 degrees Celsius by a constant heat source. And you notice it's not quite the straight line that you might imagine. And I'll tell you about that. So right now, we're probably about here, so soon we'll be melting. And while the ice is heating up, it'll heat up at a rate of 2.05 joules per gram per degree Celsius. That is, it'll take 2.05 joules to heat up 1 gram of ice up 1 degree Celsius. Now if you were to cool that down by 1 degree Celsius, you would get 2.05 joules of energy back. And this number is ice's specific heat capacity. All substances have this property and in differing amounts. For example, we'll get to water later, and that actually has a pretty high heat capacity, 4.18 joules per gram per degree Celsius. But this metal here, it gets hotter much more quickly, but it'll also cool down that much more quickly because it has a low specific heat capacity. Alright, what's the temperature now? Still says it's -1 degree Celsius. But let's check what's going on. Alright, still ice. And it's been about 2 minutes. Sorry, I'm just messing with script here. I'm not doing this from memory. Looks like it's starting to melt already. Alright, let's check it out. Oh yeah, looks like we have some melting. Now, when this is done right, the ice is supposed to be at 0 degrees Celsius while it melts, because all the thermal energy is going to break the intermolecular forces that hold the molecules together as a crystal. And when it gets enough energy, then it breaks apart and becomes liquid. It's occurring pretty fast here, and it'll be done pretty soon. Alright. Let that melt. So, as the little graph shows, right now we're melting, so we're supposed to be about this little plateau. And that represents how the temperature is not going up while it's still melting. So once that's done, then we'll be on this little rise up here. Now, I did mention before that we're on the plateau right now where it's melting. That's one of the reasons why you don't want to eat snow, because your body can't use the snow in its solid form. It has to melt it first in your stomach, and that takes a bit of energy, which happens to be more than what you get for using the water that you melt from the snow. So that's why we heat up our snow first before we drink it. Now, so not only does ice have a specific heat capacity, it also has this thing called heat of fusion, in which it takes a certain number of joules to melt 1 gram. For ice, it happens to be 334 joules per gram of ice to melt it into water. So that's a pretty high number, but vaporizing it will be much more energy intensive. Alright, it's almost all melted now, so we're pretty much heating water at this point. The probe says water's about 20 degrees Celsius. And so the ice we only had to heat up to like 0 degrees Celsius from -1, and then we had to melt it. But for water, we're going to have to heat it from 20 to 100 degrees Celsius. That's going to take a lot longer. So just sit back and watch. Now, one reason why it's going to take this long is because, as I mentioned before, water in its liquid form has a specific heat capacity of 4.18 joules per gram per degree Celsius, more than twice that of ice. So we're about here on the graph, and it'll take more energy. So not only do we have to go up 100 degrees or so, we're going to have to deal with the specific heat of water. Pretty soon here I'll be switching temperature probes, because this is actually a roasting thermometer, and it's going to beep at me once it gets high enough, and that's going to be annoying when we get to the boiling point. I'll make the switch at 70 degrees Celsius. Right now it's about 60. Alright, 68 degrees Celsius. 11 and a quarter minutes after. I'm going to go switch probes now. Degrees Celsius. My hand's getting hot, holding this thermometer down. It's been 14 minutes since we started. Soon we're going to start boiling, and we're not going to stop until all this water boils away, which I assure you will take a long while. Alright, definitely got some steam going. at boiling point now. It's getting a bit hot to measure. Alright. So, like at the melting point, water also has a heat of evaporation, which is evaporation's when the water boils into steam. So right now we're on this long portion here, and that's because water's heat of evaporation is 2.26 kilojoules per gram. Yes, that is 2,260 joules per gram of water, just to make it boil into steam. And if you do the math, you'll see that's several times more than the heat of fusion, which is for melting ice into water. And if I were able to capture this steam and heat it up further, I'd find it'd be much easier than turning it into steam. But I'm just letting it go into the air. So, well, I mentioned that with the ice, it stays at 0 degrees Celsius while it melts. Well, similar thing happens with water when it's boiling. It stays at 100 degrees Celsius until it turns into steam. And that's because all the thermal energy coming from the stove is, instead of increasing its temperature, it's increasing the kinetic energy until it can break free of the intermolecular bonds that hold it together as a liquid. And, well, breaking free of all intermolecular bonds is much harder than simply breaking free of them enough to slide around instead of standing still. Alright, how long has this been taking? Alright, we're at the 17-minute mark, and we're boiling. I'll put the lid on, see if I can accelerate the process. So for those of you that have been camping sometime, you might have had a meal where you boil the food in order to cook it. And that works because the water doesn't vaporize until it's reached that certain kinetic energy. It doesn't just vaporize at 100 degrees Celsius. So that allows you to boil things in water without having to worry about all the water going away and then having the food sit on a metal pot and burn. So it's a good thing that we have these plateaus on the graph. Alright, now we're at the 18-minute mark. Let's see how much water's left. Alright, we still have a bit of water left, but it's boiling away. So maybe you were wondering, does this process work in reverse? Well, actually it does. If I were to capture all this steam, and then condense it back into water, and then freeze it back to -1 degree Celsius ice, theoretically I would be able to get all of the energy that I put into it in order to melt it and then to boil it. And that's because of the law of conservation of energy, which says that in chemical reactions, the energy is neither created nor destroyed. It just changes forms. Alright, we're getting close to 20 minutes. A few more minutes until I check again, just because it boils faster with the lid on. So some of you may be sitting here thinking, what are these joules that I'm talking about? Well, a joule is a basic unit of the metric system, and it's a measure of of energy. And, well, you can convert joules into calories at a 4.18 to 1 ratio. And some of you might recognize that as the specific heat capacity of liquid water. And that's no accident. A calorie, lowercase c, is the amount of energy that it takes to heat up 1 gram of water 1 degree Celsius. And the calories in food are actually kilocalories. There are thousands of these little calories, just so you don't get confused. Alright, we're nearing 22 minutes. We still have steam coming out. So earlier I mentioned this third slope, and as I said, and since I can't capture the steam, I can't demonstrate, but if I were to keep the steam in a container and heat it up, I would be able to do so at its specific heat capacity of 2.08 joules per gram per degree Celsius, which is only a little more than heating up ice. And in this experiment, they had a closed container so they could trap all the steam and heat it up to 200 degrees Celsius. So that's why it goes up. Here's something interesting you might want to know. The boiling temperature of water is actually dependent on your altitude above sea level. The higher you are, the lower temperature the water can be before it starts boiling. So that means it's easier to boil the water, but if you're trying to cook food, then your food only cooks at a lower temperature than normal. That's one reason why they have directions for high altitude cooking on some baking mixes, like if you're making brownies or cake. And that's because the pressure of the air helps determine the boiling temperature of water. The more pressure there is, the more energy the water molecules have to have before they can break free and go up into the air. But since this is pretty close to sea level, it's pretty much going to be 100 degrees Celsius until it all boils out. Alright, I'm going to check now. Oh. Looks like there's somewhat less water, but still going to be a while until it all boils out. Once it all boils out, I'm going to turn off the stove because it would be bad for the pot if I heated it without any water inside. So, maybe you're wondering, why does it take kinetic energy to melt ice or to evaporate water? Well, it's because both of those reactions are actually endothermic in nature. When you do the reaction, it absorbs energy so that it has a higher net energy. Now, there are lots of reactions that are exothermic in nature, like explosions are definitely exothermic. Once you create one, it all combusts, and then at the end you have a pile of ashes which have a lot less potential energy than the explosives that you had beforehand. And condensing steam into water and freezing water into ice are actually exothermic as well. It might be counterintuitive, but in fact, energy of the substance is lowering, you just might be feeling it a little because the heat has to go out of it in order for it to lose energy. Now, if this kind of stuff interests you, there's a field of science called thermodynamics which studies this sort of stuff with thermal energy and other kinds of energy. You'll also get a basic run-through of thermodynamics when you take a chemistry course, and you can learn about it in a chemistry book. Actually, in truth, I'm doing this demonstration for a chemistry class myself. So, this demonstrates my knowledge of the subject. So, in the future, you might want to do one of these as a demonstration for your chemistry class to show that you know thermodynamics in and out. So, I'm putting in all this energy to boil this water, and maybe you don't know where it comes from. Well, this fuel bottle contains a lot of white gas, and it's fed through a pipe, and then it's combusted to produce heat energy. And the byproducts of that are some gases, including carbon monoxide. So don't try this indoors without good ventilation, or else you might suffocate. In fact, you might want to have your parents around before you play with fire at all, or else you might get burned seriously and require a medical visit. So you may be wondering, why would somebody boil all the water away? Well, there's a purification process called distillation in which they do exactly that. They take some water that's not necessarily clean, they put it in a container, and then they heat it up until the water boils away. And then they capture the steam, it goes through a cooling tube, and then it gets cooled down and condenses, and then it drops into a container. And that works because not all things have the same boiling temperature. So all those contaminants in the water have a much higher melting or boiling temperature than water. So the water goes away first. So if you can capture that steam, then you have some clean drinking water. And that's exactly what distilled water is. It's water that's gone through that process of boiling and condensing. So we're getting near the end of this demonstration, and I'd like to thank some people for making this possible. My father's the one manning the camera, so he controls when it zooms in and such. And my chemistry teacher assigned this for me. His name is Mr. Holmes, so you can thank him for compelling me to do this instead of boring you with a PowerPoint. Because I know that PowerPoints are so boring if they're not done very well. So that's why I decided to boil some water for you guys. Now another use for boiling water is to cleanse it of all those little microbes that could get you sick. That's the reason why when you're dishwashing, one of the first things you do is boil a pot of water, so then that makes it clean. And then you use that boiled water as rinse, and you also pour out some of it into another pot as your soapy water, then you add soap. But you need clean water so that you don't get sick either from the soap that you just put on your dishes or from whatever was in that stream from which you drew the water or melted the snow. Yes, boiling the water is definitely the longest part of this presentation, so bear with me. much done. I better turn this off. It's actually a tiny bit of water left. But yeah. That took close to 49 minutes. Just heat up ice and boil it all. Thank you for watching, and I hope you've learned a thing or two from this presentation. Goodbye.